In this video, we proceed to more examples that have to do with computing probabilities related to the sample mean. So for the first example, we're told that the length of time taken on the SAT for a group of students is normally distributed with a mean of 2.5 hours and a standard deviation of 0.25 hours, which means we're starting out here with a parent distribution that is normally distributed with a mean of 2.5 and a standard deviation of 0.25 hours. Now we're told further that a sample of size 60, which means in this case we're looking at n equals 60, the size of the sample, is drawn from the population. We're to determine the sampling distribution of the means. This is just meant to take us back. So in this case, no probability question, just to determine the sampling distribution of the sample means. The sampling distribution, also called the derived distribution. And this is going to mean that since we're starting out with a normal distribution for the variable x of interest, the resulting distribution will also follow. It will also be a normal distribution. It will give birth to a normal distribution. They will share exactly the same mean. However, the standard deviation will differ. So this is the mean of the sample mean, and this is the standard deviation of the sample mean, also called the standard error, and it is equal to the population standard deviation divided by the sample size. And that will be equal to 0.25 divided by the square root of 60. And that will be equal to 0.03227. So I have answered that question. The sampling distribution of the sample means will be x bar that follows the normal distribution with a mean of 2.5 for the sample means and a standard error of 0.03227. With that question completed, we proceed to the next page. In this example, we're to suppose that 9 items are randomly sampled from a normally distributed population with a mean of 100 and a standard deviation of 20. So which means the parent distribution in this case is normal, the mean is 100, and the standard deviation is 20. Let's write that in full for the original distribution. Then from this population, 9 values were randomly sampled, and these are those sampled data values. Now, this tells us that the sample size n is equal to 9. What does this question require? We have to calculate the probability, I'm going to write that as P, of getting a sample mean that is smaller than the sample mean for these 9 sampled values. So we have to calculate the probability of getting a sample mean that is smaller than, less than, the sample mean of these 9 sampled values. So what is the sample mean of these 9 sampled values? Let me write this clearly. So this descriptor here, the sample mean for the 9 sampled values, will be to add up all of these data values, 125, 95, up until 110, and divide by 9. This is the probability we want to find. Step 1, I'll find probability of x bar. I'm interested in what is the actual sample mean for these values. If you compute this, you should get 95. So we want to compute the probability of sample mean less than 95? Well, since this is connected to the sample mean, we will need to get the derived distribution of x bar, which means I need to find the mean of x bar. Remember, this will share exactly the same mean as the parent distribution, 100. However, they will differ by the standard deviation. So the standard deviation of x bar in this case will be the original population standard deviation divided by the square root of the sample size. And that will be 20 divided by the square root of 9, which will give 6.66667. Okay, now that we have the descriptors of the sampling distribution of the sample mean, I will need to locate 95. 95 is a number below 100, so 95 is here. And am I interested in below or above? The less than tells me I'm interested in below. So in this case, I can take these two parameters to my normal distribution calculator. So I'm going to go back to my normal distribution calculator. I'm going to key in the mean. The mean in this case is 100, and the standard error is 6.66667. And from the question, I have 100 and this value already keyed in. I want 95, the number below 95. So going back, I'm going to go to below 95, and hit the enter button. And you have the final answer. The probability is 0.2266. So I have the final answer there. This probability size is equal to 0.2266. And we proceed to the next example. In the next example, we're told that elevators are required to have weight capacities posted. If the weights of US men are normally distributed with a mean of 194.7 pounds and a standard deviation of 32 pounds, what is the probability that a random group of 10 men who enter an elevator will have a combined weight greater than the weight capacity of 2,000 pounds that is posted in that elevator? In order to answer this question, the first step is to note what was said in the question, that the weights of US men are normally distributed with this mean, 194.7 pounds, and a standard deviation of 32 pounds, which means the original population I'm working with, or the parent distribution here, has a normal shape, the normal distribution shape, and its mean is 194.7 and the standard deviation is 32.0 pounds. Now, the question is, what is the probability, capital P, that a random group of 10 men who enter an elevator will have a combined weight greater than the weight of 2,000? So we want probability that combined weight of a sample of n equals 10 men is greater than the 2,000 pounds that is posted in the elevator. Well, in this context, we do not have the distribution of the combined weight. What we have is the distribution of the individual weights of US men in the original parent distribution. So what we'll try to do is reconfigure this question in terms of what the average weight of a typical man is. So in this case, we'll look at the probability that the average weight of one of the 10 guys is greater than, take note, if all 10 of them, we're considering 10 of them, on average, if they're going to meet this specification, it will be 2,000 divided by 10 for one of them on average. So I have converted the question from a combined weight question to an individual average question. So in other words, this will be probability that the average weight of each of the 10 men is greater than 200. Again, just to emphasize, if we're going to meet this event or the conditions of this event, that the combined weight of the 10 men is greater than 2,000, then we're saying that on average, each of them might be greater than 200. So in this context, by converting this question to this form, I can derive the distribution of X bar. Remember, they will share exactly the same mean, 194.7, but the standard error will differ. It will be the standard deviation divided by the square root of n. What is the standard deviation earlier? The standard deviation was 32. I'm going to write that there. And then the sample size here is all 10 men. So 32 divided by the square root of 10. This will be equal to 10.119. So with that, now that I have the two descriptors of the average, I can take that to my normal distribution calculator. So going back to my normal distribution calculator, I'm going to key in the mean and the standard deviation. So now I have the mean and the standard deviation here, and I am interested now in the region whose probability I would like to compute. This concerns the number 200, that should be somewhere here. And I'm interested in above, that is to the right, greater than. So let me shade that area, and I have the required probability here. So I'm going to go back to my calculator, and I'm interested in above 200. Enter. So I have 0.3002, and that is my final answer there. So the probability that the combined weight of 10 US men that is greater than 2,000 is equal to 0.3002. Then we proceed to the next example. This says that the length of time in hours, which is the variable of interest, it takes an over 40 group of people to play one soccer match, is normally distributed with a mean of 2 hours and a standard deviation of 0.5 hours. So the parent distribution here starts off as a normally distributed population with a mean of 2 hours and a standard deviation of 0.5 hours. Then a random sample size of 50 is drawn from the population, so n is equal to 50, and we're required to find the probability, capital P, that the sample mean, x bar, is between two values, 1.8 and 2.3 hours. So this time I will need to adjust this. This will be between 1.8, 2.3, and I'm squeezing it in between. This is a probability concerned with the sample mean. So I will need to derive the sampling distribution of x bar. That would entail two steps. Finding the mean. It will share the same mean as the parent distribution. However, the standard error would be the parent standard deviation, 0.5, divided by the square root of the sample size, which is 50. So the standard error is equal to 0.15811. And now that I have the mean and the standard error of the sampling distribution, I can then focus on the fact that I want to deal with two numbers. It's 1.8, that's a number before 2, and 2.3, that's a number after 2. So let me erase this, and I would like to find the probability squeezed in between those two values. This will be equal to, let's go back, you're going to key in the mean and the standard deviation. So I have the mean and the standard deviation here. And next, I would like to find the probability between 1.8 and 2.3. So I'll key that in between 1.8 and 2.3. Now recalculate that. This gives 0.8682, and that is my final answer there, 0.8682. Done. So we proceed to the next question. In the next question, we are told that according to the Centers for Disease Control and Prevention, the CDC, the mean total cholesterol level for persons 20 years of age and older in the United States from the years 2007 till 2010 was 197 milligrams per DL. What is the probability that a randomly selected adult from the population will have a total cholesterol level less than 181 mg per DL? Use a standard deviation of 35 mg and assume that the cholesterol levels for the population are normally distributed. So, if we're assuming that we're starting off with a normally distributed population for the original mean, in this case then, we're starting off with a parent distribution whose mean is 197 according to the question, and whose standard deviation is 35. And with that given, we're to find the probability. So what we want to find is the probability that the total cholesterol level. Take note, in this case, this is just about the amount of cholesterol level, not the average this time. So, and this X is the variable of interest that accounts for the cholesterol level in a randomly drawn per adult in the US. So this would be the probability that X is just simply less than 181. Take note here that the purpose of this example is to show you the difference between the problems we considered in Module 6 under the normal distribution and the ones we're considering here. You observe that in this case, since the question is just talking about the cholesterol level, I am not deriving any distribution. I am using the original population distribution. So, in this case, I want to find the probability of X less than 181. I will locate the number 181, which is below 191, and I'm interested in the area below 181. So this will be equal to, going back to my normal distribution calculator, I'm going to key in these two values, 197 and 35. So here we go, 197 and 35. These are the parameters of that distribution, and in relation to that distribution, I'm interested in below 181. So for below, I'm going to click on below 181 and hit the enter button. I have 0.3238. So 0.3238. Then for question B, what is the probability that a randomly selected sample of 150 adults, so n equals 150, from the population will have a mean total cholesterol level less than 181? We're going to use the same parent population standard deviation. So in this case again, we're starting off with this parent population, but the difference is this. In this case, it was just about the total cholesterol level. This time, it's about the mean total cholesterol level. So in this case, the probability is concerned with the sample mean, X bar, being less than 181. The goal here is to strike a difference between when we're computing probabilities with just X and probabilities connected with the sample mean, X bar. So in this case, since it is probability connected with X bar, I will need to generate the sampling distribution of X bar. In this case, also, I will need to get the mean of X bar. It will share the same mean, and as we have done earlier, it will not share exactly the same standard deviation. Rather, it will be the standard deviation divided by the square root of n. So that will be 35 divided by the square root of 150. And that is equal to, this is equal to 2.857738. So I can take these values, and this will be the parameters of the distribution, of the sampling distribution, rather. And I'm interested in values connected with 181, so I will locate 181, and I would like to find the probability lesser than 181. So right here it is, and let me take that back. So this will be equal to, I need to key in the parameters, so I'm going to do that. So go back to my normal distribution calculator. The mean will stay the same, however, the standard deviation will be different. So here on the screen, you can see I now have the adjusted standard deviation based on the fact that we're computing probabilities associated with the sample mean. And I'm interested in below, the area below 181. So going back, I am interested in the area below 181, and hit the enter button. So, which indicates that the area is really tiny. This is equal to 0. So with that question completed, we've come to the end of that part of this module, where if the parent population is normal, then the derived distribution is always normal too. They will share the same mean, but they will have different standard deviations. In the next video, we are going to consider how we deal with situations where the parent population is not normally distributed. Do we follow a similar procedure? If we are going to follow a similar procedure, under what conditions are we allowed to do that? Again, in the next video, we're going to consider what happens if the parent distribution is not normally distributed. How do we compute probabilities connected with the sample mean?